Hello students, welcome to my channel. This video content is mainly for B.Sc Mathematics Honours. Today our chapter is integers or number theory, which is taken from the block Classical Algebra. In this video, we are going to look at the principle of mathematical induction with proof. Okay, so let's get started. Principle of mathematical induction or principle of induction. It is also called the first principle of mathematical induction. Okay, there is another principle called the second principle of mathematical induction, which will be discussed in another video. Alright, the principle of mathematical induction has two forms. Here is the first form. Let S be a subset of n. Here n means the set of all natural numbers, that is n equal to 1, 2, 3 ... Okay, let S be a subset of n such that 1 belongs to S and k belongs to S implies k plus 1 belongs to S. Then S is equal to n. Okay, now we are going to prove this. To prove S equal to n, what do we have to prove? Notice that we have S subset of n. So to prove S equal to n, we have to prove n subset of S. Why? Because we know that S equal to n if and only if S subset of n and n subset of S. Okay, we have S subset of n. So to prove S equal to n, we have to prove n subset of S. Clear? Again, to prove n subset of S, we have to prove n minus S equal to what? Suppose this is n and this is S. N subset of S. Notice that here n minus S contains nothing, that is n minus S equal to phi, the empty set or null set. So to prove n subset of S, we have to prove n minus S equal to phi. Okay, now we start the proof. Let t equal to n minus S. We have to prove n minus S equal to phi, that is t equal to phi. We shall show that t equal to phi. Okay, if possible, let t not equal to phi. Then t is a non-empty subset of n. Okay, t is a non-empty subset of n. Why subset? Because t equal to n minus S, this is equal to the set of all x belongs to n such that x does not belong to S, and this is clearly subset of n. Belongs to n implies subset of n. Okay, so t is a non-empty subset of n, and hence by the well ordering property of n, by the well ordering property of n, T has a least element. Okay. Now what is least element and what is the well ordering property of n? Least element. Let S subset of n and A belongs to S. Then A is said to be a least element of S if A less equal to X for all X belongs to S. That is the lowest number of the set. Okay, we can say the least element instead of a least element because least element is unique. For example, the least element of the set S equal to 3, 5, 7, 9. The least element of the set 3, 5, 7, 9 is what? 3. The lowest number of the set. Okay. Now, what is the well ordering property of n? Well ordering property of n. Every non-empty subset of n has a least element. Every non-empty subset of n has a least element. Okay, this is the well ordering property of n. Now come back to the proof. T is a non-empty subset of n and hence by the well ordering property of n, T has a least element. Say m. Okay. Now from the given condition, from the first given condition, we have 1 belongs to S. Since 1 belongs to S and m belongs to T and m belongs to T and T is what? T is equal to n minus S. Since 1 belongs to S and m belongs to n minus S, we have m not equal to 1 and m belongs to n. Okay, can you say this? M not equal to 1 and m belongs to n. Suppose this is n and this is S. This is n and this is S. So this is n minus S. Now 1 belongs to S and m belongs to n minus S. 1 belongs to S and m belongs to n minus S. Clearly m not equal to 1. 1 belongs to this and m belongs to this. So m not equal to 1. So we can say m not equal to 1. Again, m belongs to n minus S. Subset of n implies m belongs to n. M belongs to n minus S and this is subset of n. So m belongs to n. So we can say m belongs to n. So we have m not equal to 1 and m belongs to n. That is that is m greater than 1 and m belongs to n. Can we say this? M greater than 1, we have m not equal to 1 and m belongs to n. We know that every element of n is greater than or equal to 1. Since m belongs to n and m not equal to 1, so m must be greater than 1. So we can say m greater than 1. Okay. Now m greater than 1 and m belongs to n. So m equal to 2 or 3 or 4 or ... Okay, that is m minus 1 equal to 1 or 2 or 3 or ... So m minus 1 belongs to n. So from here we can say m minus 1 belongs to n. Therefore m minus 1 belongs to n. Clear? Again, since m is the least element of T, m minus 1 does not belong to T. Okay, can you say this? Since m is the least element of T, m is the lowest number of T, but m minus 1 is less than m, so m minus 1 does not belong to T, and T is what? T is equal to n minus s. Okay, so we have m minus 1 belongs to n, but m minus 1 does not belong to n minus s, and hence m minus 1 belongs to s. M minus 1 belongs to n, but m minus 1 does not belong to n minus s. So m minus 1 belong to s. Okay, so we have m minus 1 belongs to s. Therefore by the condition 2, m minus 1 plus 1 belongs to s. How do I get this? Recall the second given condition. From the second given condition, k belongs to s implies k plus 1 belongs to s. Therefore m minus 1 belongs to s implies m minus 1 plus 1 belongs to s. So we have m minus 1 plus 1 belongs to s. That is m belongs to s. Okay, which contradicts the fact that m belongs to what? M belongs to s contradicts m belongs to what? Suppose this is n and this is s. So this is n minus s. So m belongs to s contradicts m belongs to n minus s. Because s and n minus s are disjoint. Okay, so m belongs to S contradicts m belongs to n minus S. That is, m belongs to T. Clear? Thus, we arrive at a contradiction. So, our assumption is wrong. That is, T not equal to phi is wrong. Therefore, T equal to phi. Okay. Now, what is T? T means n minus S. So, n minus S equal to phi. N minus S equal to phi. That is, n minus S contains nothing. So, n and S look like this. Suppose this is n and this is S. Clearly, n is contained in S. That is, n is a subset of S. Okay. Hence, n is a subset of S. Clear? Now, given that S is a subset of n, since S is a subset of n, it follows that S equal to n. S subset of n and n subset of S implies S equal to n. Okay? This completes the proof. So, we have proved the first form of the principle of mathematical induction. Now let's look at its corollary. Okay, so here is the corollary. Let Pn be a statement involving n. Here, statement involving n means what? Let me explain with some examples. We know that 1 plus 2 plus 3 plus ... plus n equal to, this is equal to what? N into n plus 1 by 2. This is a statement involving n, and this statement is true for all natural numbers n. Okay, we can call it Pn. So Pn is the statement 1 plus 2 plus 3 plus ... plus n equal to n into n plus 1 by 2, and Pn is true for all natural numbers n. Clear? Another example is factorial n greater than 2 to the power n. Factorial n greater than 2 to the power n. This statement is true for all natural numbers n greater or equal to 4. Okay, now come back to the corollary. Let Pn be a statement involving n such that P1 is true and Pk is true implies Pk plus 1 is true, where k belongs to n. That is, k is a natural number. Then Pn is true for all n belongs to n. That is, for all natural numbers n. Okay, now let's look at how to prove this. First of all, we have to take a subset S of n, we have to take a suitable subset S of n such that S satisfies the two conditions of the first form of the principle of mathematical induction. Let S equal to the set of all n belongs to n such that Pn is true. Then S is a subset of n, because here we have belongs to n, so S is a subset of n. Okay, such that now we have to check whether S satisfies the two conditions of the first form of the principle of mathematical induction. That is, we have to check whether 1 belongs to S and K belongs to S implies K plus 1 belongs to S. Okay? Notice that from the first given condition we have P1 is true. So from here we can say 1 belongs to S, because Pn is true implies N belongs to S. So P1 is true implies 1 belongs to S. Okay? So we have 1 belongs to S. And this is obtained by the first given condition, that is by the condition 1. So S is a subset of N such that 1 belongs to S, and this is number 1 belongs to S, and number 2 K belongs to S implies, what will we get here? K belongs to S implies what? From here K belongs to S implies Pk is true. So K belongs to S implies Pk is true. Okay, and from the second given condition we have Pk is true implies Pk plus 1 is true. So this implies Pk plus 1 is true. Again, from here Pk plus 1 is true implies K plus 1 belongs to S. So this implies K plus 1 belongs to S. So we have K belongs to S implies K plus 1 belongs to S. K belongs to S implies K plus 1 belongs to S. And this is obtained by the second given condition, that is by the condition 2. Okay. Thus, S is a subset of N such that 1 belongs to S and K belongs to S implies K plus 1 belongs to S. Clearly, S satisfies the two conditions of the first form of the principle of mathematical induction. This is the first condition and this is the second condition. Okay? Therefore, by the principle of mathematical induction, therefore by the principle of mathematical induction, what can we write here? S equal to N. Okay. Now N belongs to N implies N belongs to S, because we have S equal to N. So N belongs to N implies N belongs to S, and this implies what? N belongs to S implies Pn is true. So this implies Pn is true. Thus N belongs to N implies Pn is true. That is, Pn is true for all N belongs to N. Hence Pn is true for all N belongs to N. Okay, this completes the proof. So we have proved the corollary of the first form of the principle of mathematical induction. Now we are going to look at the second form of the principle of mathematical induction. Okay, so here is the second form. Let S be a subset of N such that N0 belongs to S and K greater equal to N0 belongs to S implies K plus 1 belongs to S. Then S equal to the set of all n belongs to n such that n greater equal to n0. Okay, now let's look at its corollary. Let Pn be a statement involving n such that Pn0 is true, where n0 belongs to n, and Pk is true implies Pk plus 1 is true, where k is the natural number greater equal to n0. Then Pn is true for all natural numbers n greater equal to n0. Alright, now we are going to look at the similarities between the two forms of the principle of mathematical induction and their corollaries so that we can remember them easily. Okay, so this is the first form and this is the corollary of the first form. This is the second form and this is the corollary of the second form. Now notice that here we have 1 belongs to S and here P1 is true. Here K belongs to S implies K plus 1 belongs to S, and here Pk is true implies Pk plus 1 is true. Here we have N0 belongs to S and here Pn0 is true. Here K greater equal to N0 belongs to S implies K plus 1 belongs to S, and here Pk is true implies Pk plus 1 is true, where K is a natural number greater equal to N0. Okay. Also notice that if we put n0 equal to 1 here, then we get this one, and if we put n0 equal to 1 here, then we get this one. Okay, so this is how we can remember this easily. Alright, so that's it. If you have any questions, you can ask me freely in the comment section and I will definitely try to answer them. If you like this video, please click on the like button and also subscribe to my channel for more math videos which are important for B.Sc math exam. And don't forget to click on the bell icon that will give you notifications when new videos come out. So thank you so much for watching and until next time.